Hello, I'm Karidi from Spark Beyond, and in this talk, I want to touch on the challenge of teaching machine thinking and creativity. It's almost impossible to mention this topic and not refer to the revolution we're experiencing with transformers and deep neural networks, in particular GPT-3. Yet the paradigm I will present today was born already in 2014 and is anchored in a semantic approach, attempting to address the strengths and weaknesses of human thinking and creativity. So what makes some problems harder to solve than others? A dominant factor is the richness of the problem space. When the problem involves multiple resources, processes, and control parameters, it creates an overwhelming number of ways to connect them, which results in us researchers defaulting to our individual biases and personal experiences. It becomes even more complex when the problem is at the intersection of multiple domains of knowledge, and even more so when the solution requires blending information and knowledge from one or two or more disciplines. Expert collaboration then becomes a bottleneck and is at the critical path to breakthroughs. So yes, we have limitations. We think not so fast. We can come up with new ideas. Sometimes we can articulate them in minutes. Sometimes it takes a little more. Coming up with the next good idea may take days or weeks. And evaluating whether the idea is good or not sometimes requires setting up an experiment, writing a computer program, and that, of course, takes just minutes. So what we need is a machine that doesn't have the same limitations, that can generate millions of ideas in minutes, and then proceed to autonomously test them, rank them, discover which ones are better supported by what we know and the data that we have, and which ones are less. This machine will be able to connect the dots much better than us and be less affected by our own biases and experiences. You remember when you try something very hard and it fails, sometimes it hurts your motivation. Our machine wouldn't be so much affected. So we're going to empower researchers with a machine that can not only generate ideas, rank them, but also suggest to look for new data or experiments that can refute our current theories and challenge existing practices. Here's an eye-level diagram that tells us how this process will work. The researcher will describe the problem, and we will touch on how that happens. The machine will take the problem, synthesize millions of ideas. It still doesn't need much in order to generate these ideas, but keep in mind that some of them will be good ones and some of them will be less good. In order to do a reality check and evaluate the ideas, the user needs to upload data. The machine will automatically write code, run it on the data, evaluate it, and produce a ranked list of the ideas. So we need to figure out how to translate the problem in its domain to a language that the machine understands. We noticed that problems companies have are often about optimizing KPIs, such as profit, retention, or payment default rate. In the next few slides, we will drill down to the example of a store chain looking to open their next 10 branches. Other problems companies face are strategy problems, and some of them are companies that are looking for inorganic growth or M&A and acquisitions. So when we come and translate, we try to present the machine with a semantic model that is built of entities, attributes, and functions that allows the machine to start generating ideas. What about the problem itself? The problem that we mentioned just one slide ago, a store chain looking to open the new branches, can be articulated and presented in different ways. We can look at a classification problem that would be, let's distinguish the profitable stores from the not profitable ones, or a regression problem, which would be what increases and decreases the profit in our stores. We will also treat time differently depending on whether we're developing a 5-year strategy or looking just for the next 1, 2, or 3 branches. So when we come to model the problem, in this case, we will have to talk about branches, their location, floor size, P&L, transaction, inventory, employees, and so on. And in order to express ideas, we will need not only these nouns, but also verbs. These are functions that we can apply to the entity objects. For example, the time since a particular date, that helps us define age. The revenue per employee is obviously something that can be used in understanding the problem, and the distance to the nearest competitor branch might be a relevant factor. Now the machine takes the entities, the functions, and generate ideas. You'll recognize that complex hypotheses can be created by composing and combining various functions and entities. For example, the distance to the nearest object of type coffee shop. Sometimes it is actually the right parameter that makes this idea better than others. The distance to the nearest coffee shop is, of course, more meaningful for a bookstore chain than the distance to the nearest tree. And this is also why such an insight would lead not to only look for locations that are close to coffee shops, but some bookstore chains may decide to open a coffee shop inside the branch. Here is a real-world example of how fuel consumption was actually reduced by 10% after taking actions driven by insights the engine discovered. The engine doesn't only discover insights, it can quantify them, which will help managers prioritize the actions associated with each of these insights. In this particular case, let's focus on 2 insights. One of them was that preventing engine idling at low revolution can save 5% on fuel consumption. How do we deal with this? We run driving workshops with our drivers and measure the impact after a few weeks or months of driving according to the new recommendations. This company was able to prove and demonstrate actual savings of about 10% just using these insights. Here, the company was able to reduce subscribers churn by 30% in 3 months. The driving insight, one of the driving insights, was the realization that the iPhone app used by users to read news was broken on some pages. Fixing it helped retain those users. So this isn't science fiction. We built this machine, we call it the hypothesis engine, and it automatically writes the code to test each of the hypotheses, runs many hypotheses, thousands of hypotheses at a time, and calibrate to the next set of hypotheses that needs to be assessed. So not only the data helps us distinguish the good ideas from the not so good ideas, it also helps us navigate this infinite space of hypotheses and choose where to look for the next one, which of the next 1,000 hypotheses we want to evaluate. In fact, you can think of this as a search engine, an engine that crawls the space of all possible hypotheses, writes all possible programs and runs them on the data, and uses the data to optimize the navigation in this huge space. And what if we have no data? So that happens very frequently. We're developing a new product. No one has used the product. We don't have any usage data that we can apply hypotheses to and rank order them. So how we can generate a different paradigm that can still create many hypotheses, evaluate them, rank order them, and help us deal with these situations. Let's take an example. We want to make sustainable agriculture more prevalent in third world countries. The problem modeling is very similar. We need entities and building blocks. Yet, this time, some of the entities will be discovered by the engine as we go, rather than specified in advance, as we saw in the next branch to open problem. And the relations will be specified by the users that is a domain expert. In this situation, we can look at relations such as what negatively influences sustainable agriculture, what are the deficiencies of some of the solutions, what increases the efficiency, and what reduces the deficiencies. Again, the ideas will be a result of composing and combining the entities and the building blocks. Let's see what that is. On the right-hand side, you can see a screenshot of what happens when we apply the tool, this new engine, asking how we can make sustainable agriculture more prevalent. This particular chain of thought takes us from what negatively influences sustainable agriculture to a solution. Let's follow through. Each building block here triggers a search on the web and asking a question. If the factor negatively influencing sustainable agriculture is weeds, we're asking what is a solution to weeds, or what reduces weeds in real life. We take the one of the many concepts that is returned by the engine is herbicides, and we look for deficiencies. This composition of negatively influences, looking for a solution, looking for deficiencies, and then looking for another solution to deficiency. This is an idea. To make the idea concrete, we need to embed the entities, the weeds, the herbicide, and the residue. And here, the innovation comes from moving to a different domain. The solution, soft water, is actually borrowed from cosmetics. And when applied to agriculture, we get a hypothesis. What happens when we use soft water in the irrigation systems and sprinklers to wash out the residue? What actually helped us take this idea and say, this is interesting, we should look at it? It's not simply the sequencing of the nouns and verbs. It's the fact that we were able to find evidence that supports each of these steps. The claim that weeds negatively influence sustainable agriculture, then the claim that herbicides are solutions for weeds, and so on. So the analog and the generalization is that what separates the good ideas from the not so good ones is actually evidence that we find on the web or on other knowledge repositories that we connect to the engine. Can we take it even further? Can we connect both paradigms? For example, the web mining approach takes us to fertilizers. And now, can we use data to discover which fertilizers work better in relevant areas? We discovered that using sufficient amounts of nitrogen-based fertilizers had good effect on yield in third world countries. This was discovered by the hypothesis engine when we uploaded World Bank data about the use of fertilizers and the yield associated with those countries. We also saw that the effect was not as strong when potassium-based fertilizers were used rather than nitrogen-based fertilizers. Another type of problems we see often is companies looking for M&A candidates. Using the knowledge-based ideation approach, one of our clients, the automation domain, were able to expand the list of M&A candidates they constructed manually with their experts using the engine to a 5x, to a list that is 5x longer. So from something like 8 or 10 potential candidates, they got to 50 candidates. Let's recap. What we saw today is a problem-solving ideation paradigm. It is based on semantic modeling of the problem space and the ability to automatically generate ideas, representing them as sequence of compositions and combinations of verbs and nouns, the entities and the functions, and rank order those ideas by the level of support that we get from data or knowledge. Moreover, we realized that the data or knowledge not only helps us rank order the ideas, it also helps us navigate in this huge space of hypothesis to areas where we have better ideas. And when we exhaust the search in those areas, we direct to other areas, test them again, and opportunistically discover pockets of good ideas and learn how to avoid the areas of less effective ideas. You can see here a more humoristic description of this paradigm. Thank you, and feel free to send any questions.
Great. Thank you so much, Ron, for this wonderful talk. Very insightful, very big picture, as well as lots of details that we could learn so much. So let's see if we got questions. Please feel free to type in the channel, the chat channel. So we have one question. So you have mentioned that in the infinite space of a hypothesis for a given problem. So how do you visualize the space and how the engine and the user navigate the space effectively? Can you show some specific examples?
Yes, be happy to. Let's actually use the interface of the engine. You should be able to see my screen.
Yes.
Okay, I'll take an example that many of us know. This was the King County house pricing example. It's on Kaggle. It's very famous. What we see here is the original data set that has house prices in the Seattle area. We can see the price. We can see the date where this house was put on the market, and many attributes. What's interesting is that if we want to make the engine search a space with rich set of hypotheses, we want to connect additional data. And our philosophy is that data should be connected with hooks rather than by joins. So we're not creating a huge table, but we're just telling the engine you can connect the dots between your main data set to additional ones. Like here, we have the census data for the US with a lot, as you can see, demographic variables for different zip codes in the US. And we also have OpenStreetMap. Of course, I can't visualize it, but this is a database of millions of geolocations with tens of thousands of attributes for each. And now we want to look at this hypothesis space that is rendered by the engine. So this is actually created without looking at the actual data, just looking at the schema of the data. And we can see here the different sources. Let's open the census data and look here. And we can look at different census data attributes that are available for zip codes. Let's pick one, home value, and we can see a set of expressions that is taking home value, does the lookup, and applies different functions. One of these, if we click here, the engine is going to show us which feature or which insight is generating sufficient evidence by the actual data. So the engine is now evaluating the expression on the data and is looking for, is the average value threshold? Can we find a threshold for which the average home value is significantly predictive of high or low prices? And we can see that this insight, which is a very simple one, creates a great, has a support of 48% and creates a nice shift of the mean of the price. So this is how the space is mapped. We can navigate that if we just want to take another attribute. We can see additional features. And let me actually show something more interesting. We can go here to geospatial features, and we can look at the price by location. So the space here is pretty elaborate. We start from the location. We look at a geotemporal phenomena, looking at the last 30 weeks of data for that location, and we start creating expressions. We can look at the average value. We can look at the average value of the 3 closest points. We can look at the closest distance. We can take one of these and apply average, minimum, maximum, and sum. Let's take one of these as an example, and we get actually the insight, the statement that got the highest score, which is the most explanatory expression for this problem, is if we take the weighted average value of the closest 3 points for this house, and we can see that the support for that is 42%. So for 42%, the price of the closest 3 homes was very predictive of the price of this home. Not very surprising, but a very intuitive insight that happens to be one of the more, or the best, the strongest signal that we have here. We can go and look for some other other expressions. This one and move to another view. So here we can see other geospatial expressions very, very similar to this one. And if we look at the, oops, sorry. If we look at the, these are the top expressions that were found by the engine. I want to show a few of these. This tells us that if the percent of homes where the homeowner has a university degree is high, then the price is also high. And I really like two insights here. This says that if the area has few mobile homes, the price is higher. And this one says that if we are close to a bay, the price is higher. These, of course, were all generated automatically by the engine, and the fact that they stick out is because the data validated them. Do we have more questions?
Yes, we have a question that is coming through the channel also. So it says that this work reminds me of Doug Linnett's work in the 1970s or 80s on AM and Eureka, with the addition of using real data to validate ideas in the context of specific domains. Any thoughts about this? Not too sure whether you have insights about this, Ron?
I'm not familiar with this work. I would love if the person asking this question would actually send me an email. I'd love to look at this and get back to you. My email is ron@sparkbeyond.com.
That's wonderful. So another question, where we really need help is with a set of complex existential problems such as hunger, global warming, and well-being. What's your vision of how we humans will leverage AI for cracking those problems, Ron?
Yeah, I'll respond to that in a second. I read the question, the previous question here again, and my understanding is that the person is referring to work and saying that the addition in this work is that we're using real data to validate the ideas. This is important. I completely agree about the importance of validating the ideas with real data. And a very interesting point is that the real data also helps us navigate the space and choose areas and hypotheses that are more meaningful. If we use the data to actually formulate ideas that use terms from the data. For example, in this case, we took geolocations, we took the lat long of the location, we looked in OpenStreetMap and we saw that there is a bay there. If we were looking at locations in Africa, we wouldn't even look at the hypothesis that is talking about the bay, because there would be no bay. Well, there are bays in Africa, but let's say in Central Africa, we wouldn't see these hypotheses. So that's indeed very, very important. Going back to the question about the existential problems, this is definitely one of the core motivational dimensions for Sagi and I to found Spark Beyond. We had the vision that if we help machines to harness everything we know digitally, of course, we still can't have machines read our thoughts. But if we look at all the digital data and knowledge available, either by structured data, databases, and so on, as well as unstructured data on the web. And we created algorithms that can connect the dots between these and the questions that we're interested in. We can really increase the complexity of problems that we humans can solve. Now, when we look at those existential problems like hunger or energy or global warming, the challenge is that in order to really come up with novel or disruptive or new ideas with this context, we need to connect to multiple domains of knowledge. And that would require a few steps that we still can't do with the engines that we've built. So our vision is that definitely machines have an important role here, connecting the dots between different domains and decomposing problems into smaller problems and simpler problems that we can either solve with human researchers or have AI agents to solve, is at the core of that vision. And one of the engines that actually two engines we're currently working on are related to that. One is, we call it Orchestrator, and it combines AI agents and human agents with the task of creating workflows to solve complex problems. And the other one is an AI agent that decomposes complex problems into simpler ones. It's a race. Are we going to do it fast enough? Let's hope so.
Wonderful. Let's see if there's any other questions before we close it. I don't see that in the channel anymore. And I think, okay, there's one question that I just see. Can you please elaborate the difference between join and hook, especially when running predictions? How does hook differ from join?
Mm-hmm. Oh, that's a good pragmatic question. If we end up joining the data sets in order to navigate composite hypothesis on the joint data set, we are running into a few problems. One is that there are many ways to join a set of, even a small set of data sets, and that will create a memory / storage overflow very, very quickly. We also will end up joining data that never gets visited by the hypothesis search because it doesn't yield any signals. And the compute and search time that is anyway not trivial will become computationally impossible to support. So the reason to apply our different approach, which is we connect data on the fly as we construct the hypothesis, helps us simply contain this infinite space as we go.
Okay.
Maybe I can explain it even better. The challenge is we don't know which areas of this space we will visit. The navigation in the space, the algorithm navigates the space according to the signal that it finds, and then it only creates the code to connect the dots or to do the join that is necessary for evaluating that particular path of hypothesis.
Let's see. Wonderful. Thank you for this very engaging conversation. I'm glad we get the time to ask several of those questions around, and I'm glad that also you and Sergey are thinking about the problems that's much important. And I think lots of those problems actually are very right next to us, global warming, hunger. So my best wishes for you and for your entrepreneurship pursuit. And let's thank you for coming to KDD and give us this talk. And thank you for our audience for a good set of questions. Please contact Ron if you have any follow-up questions. You will get very thoughtful answers. I know that. Thank you, Ron, again. Thank you.
Thank you. Thank you.
Yeah, great. Thank you, Ron.
Thank you for inviting me. This was a pleasure, and hope to be talking on the next KDD.